Okay, let's study a little bit about Bayesian inference. And Bayesian inference is, of course, based on Bayes theorem, which is like this. Probability of A given B is given by probability of B given A times probability of A divided by probability of B. So this is called Bayes theorem. And we want to do what we want to do here is to kind of hypothesis testing. So let's say A is our hypothesis and B is the data or observation. So what we want to do is, based on the data, we want to calculate the probability that the hypothesis is true. Okay, so what we want to do is, so let's call this H, and let's call this D. So if we put this, what we want to calculate is something like this. Probability of hypothesis given data is equal to the probability of data given hypothesis, and probability of hypothesis divided by probability of data. Okay, but actually in practice we have some other information which are called prior knowledge, prior information. So prior information is something we already know before getting any data or before making any hypothesis. Usually we don't start from nothing, right? We start from some knowledge we already have from previous studies or someone else's experiments or whatever, or our intuition even. So all those information can be used to form our hypothesis, right? So actually everything here are based on conditioned on our prior information or prior knowledge. So these things, let's see. So this is this hypothesis condition. Everything is conditioned on hypothesis. So let's see. So this is hypothesis given hypothesis, and everything is conditioned on hypothesis, and this one also. No, I mean prior knowledge. Okay, so here D comma I means we have prior knowledge and the data. Okay, and here also we have prior knowledge and hypothesis, and based on that we calculate the probability of the data. And this probability is the probability of that the hypothesis is true given the prior knowledge I. Okay, and this one in the denominator is just a normalization constant. Formally it is the conditional probability of the data given our prior knowledge. So this is irrespective of hypothesis. In fact, this is just a normalization constant, so this means this is required so that this is a probability. The left hand side is the probability measure. Okay, so this is given by summing the numerator given hi, probability of h given I, summing over all hypotheses. Okay, in reality there can be infinitely many hypotheses, right? So for example, coin may be exactly fair, that means probability of obtaining a head is exactly zero point 0.5 or 0.15, 0.505, 0.50001, and so on. In this case, this is a continuous random variable, so it will be integral instead of summation. But the idea is there are many possible hypotheses, and we have to add them up to normalize the probability. And in practice, this may be impossible to calculate, but nevertheless, uh, formally, this is required. So based on this formulation, we try to uh, test our hypothesis or form some improved hypothesis based on data. Let's consider the problem of coin flipping again. What we want to estimate is the probability of obtaining a head. Okay. Obtaining a head of a coin. Okay, so this is a random variable that can take values between 0 and 1. Okay, so ultimately, what we want to calculate is some probability of this random variable being some particular value. Let's say, for example, something like, what is the probability of this being 0.5 exactly, given the data, given some data. Data in this case would be the number of heads out of a certain number of flips, right? But actually this p here is a continuous random variable. So as such, this probability p equal to 0.5 exactly would be 0. So this is not so useful. Okay, so what we want to calculate is actually the density. Let's call it rho. So density of this probability. So okay, let's formulate this in the way of Bayesian inference. So suppose this p has some specific value, small p. Okay, given this, so this is a kind of hypothesis, right? And let's flip the coin n times, number of flips. Then what is the probability of obtaining x heads? Number of heads out of n. So what we want to calculate is this probability. Okay, probability that the number of heads is x, given the probability of obtaining a head is small p, and the number of flips is n. Okay, so this problem is actually just a ordinary binomial distribution. So this probability should be like n choose x, p to the power of x, and 1 minus p to the power of n minus x. So this is a binomial distribution. But notice how this probability is formulated as a conditional probability. Right? It's conditioned on the value of p and the number of flips. Okay. Without these being given, this probability cannot be calculated. Okay. So this probability will correspond to this part, right? The data is the number of heads in this case, and hypothesis is the given value of p, and I, prior knowledge. For example, this may include the number of flips or anything else. Okay, so what would correspond to this part? So probability of the hypothesis given prior knowledge. So for this, we should assume some kind of probability density function for the value of p. So density of p given some prior knowledge. And in this case, let's assume that we don't know anything about this probability distribution. So we may assume it's a uniform distribution. Okay. So if you plot this, it's just a uniform distribution. Okay, it's just 1, like this, 0 and 1. So we have no assumption whatsoever about the fairness of this coin. Now it can be exactly fair, but it can be extremely unfair in favor of heads or in favor of tails. And we have no preference at all. Okay, so let's assume this as this part. Okay. Then, according to Bayes' theorem, the conditional density of this p, given that x, the number of heads is x, and the number of flips is n, and any other prior knowledge. So this density should be equal to this probability function of the binomial distribution. And rho p given I, and divided by the probability of x equal to x given n is n and I. Okay. And if you substitute all the information, we have, okay, apart from the denominator, let's just leave the denominator as it is, just PR. And this part is the binomial distribution. So it's n choose x, px, 1 minus pn minus x. And this part is just 1. Right? It's a uniform distribution. So this is the density function. It's a posterior density function of our model. So this just erase this one because it's unnecessary. And this part, this denominator, which is just a normalization constant for this density function, is sometimes called evidence. Okay, so, and we know how to calculate this in theory at least. So this is x given and I is, just integrate this one over all possible values of p. Okay, in this case, p varies from 0 to 1. So n choose x, this 1 minus p n minus x dp. Okay, so we integrate, since p is a continuous random variable, we integrate over p, then we get this. Okay, so if we put this expression into this equation, we have, actually this n choose x part will cancel out in, this is just a constant. So what we have is this. So p to the power of x, 1 minus p n minus x divided by 1, 0, 1 px 1 minus p n minus x dp. So this is the density function for p. And of course, if you want to calculate the probability that this p resides in some interval from a to b, for example, given that the number of heads were x, number of flips was n and I, then we just integrate this function. So this function from a to b. Okay, so this probability can be calculated as this. And if you remember, what is this function in the denominator? Remember? This is actually a beta function. So beta function with parameter a and b is given by this. T a minus 1, 1 minus t b minus 1 dt. So if you compare this, so this is beta function. If you compare this with this, you will notice, let's see. Okay. So this p corresponds to this t, and x corresponds to a minus 1, and n minus x corresponds to b minus 1. So this is actually the beta function with parameters x plus 1 and n minus x plus 1. Okay. So you have seen that this beta function appears very naturally in this problem. So instead of the uniform prior distribution we have just used, we could use more general beta distribution. For example, let's say our prior distribution, let's see, rho p given I, prior knowledge, is a beta distribution. Okay, so it's a density function of some beta distribution with parameters alpha and beta. 1 minus p, beta minus 1. Okay, so p is between 0 and 1. Okay, so this is another prior distribution for some alpha and beta, and they must be positive. Okay, and if you notice, if alpha a is equal to beta is equal to 1, then this is a uniform distribution. Just like we have used before, right? If you put alpha 1, beta 1, those exponents are 0, so this is just a constant. And you can show that beta of 1 and 1 is equal to 1, so it's a uniform distribution between 0 and 1. But anyway, instead of the uniform distribution, let's use this general beta distribution for the prior. In that case, we have the posterior probability as this. So probability of this given n is equal to I, p equal to p and I, and this one, rho p given I p divided by x given n and I. So if you plug in the binomial distribution here and this beta distribution here, you will have something like, so ignoring the proportionality constant, we have p to the power of x plus alpha minus 1, 1 minus p to the power of n minus x plus beta minus 1. So if you normalize this, this will be a beta distribution with parameters x plus alpha and n minus x plus beta. Okay. So what we have seen here is if you use the beta distribution as the prior distribution for this Bayes theorem, then what we get for the posterior is also the beta distribution, but with a different parameter sets. Okay, so now we have beta distribution, and we have binomial distribution, and we get beta distribution again. So in this sense, the binomial distribution and the beta distribution, they are somehow closely related. And in this particular example, beta distribution is said to be the conjugate distribution for the binomial distribution. Okay, so beta is conjugate to binomial distribution. Okay, there are many such examples, and we will see some of them later. So let us summarize. First, we had the prior distribution of P, which was the beta distribution. Okay. Then we had the likelihood So the probability of the data given given the hypothesis and other information. So this part is the hypothesis. So that was binomial distribution in this case. Then from these, we calculated the posterior. So this is prior. This is likelihood. And from this, we got the posterior probability. So it was P x plus alpha minus 1 minus P n minus x plus beta minus 1 and beta function. So this is posterior. And this is beta distribution. Alpha beta, and this is again the beta distribution, but with a different set of parameters. Okay, so beta and binomial. So this is binomial. These two distributions are conjugate distributions. Okay. One of the nice things about Bayesian inference is that we can update our knowledge as soon as new data come in. So this is called Bayesian updating. For example, in the previous example, we had the prior of the probability of getting ahead, so prior distribution without any experimental data. For example, we could have no biased information prior, so that is uniform distribution. Suppose we toss a coin once. So according to the binomial distributions, we toss a coin once, and suppose we get ahead. So that is x is 1. Okay, apply this to the Bayesian formula, Bayes theorem. Then we have the posterior distribution. So this is the first step of posterior distribution will be x1 and n1 is 1, and this will be, so if you apply the same formula, we would have 1 over probability of x1 is 1 given n1 is 1, and 1 choose 1, p1 and p1 minus p1 minus 1. So that is actually, if you calculate this, it will be 2p. So this is our posterior distribution for the probability of obtaining a head. So if you plot this, first we had a uniform distribution. So 0 to 1. And once we toss a coin once and obtain a head once, then our posterior distribution is this. So it would look like, so it's 2p, so this is p, this is density, so 2p would be like this. It's ugly, so it will be like, so this is 1, then 1, 2, 5, 6, 7. So the density would look like this. Okay, so this is 1. So between 0 and 1, this will be 2. So since we got one head out of one flip, now our experience tells us that it may be biased. This coin may be biased towards heads. But of course, our knowledge, this knowledge is based on just one experiment, so it's not very decisive. So it's still it's possible that our probability will be somewhere near 0. So it's not exactly 0 here, around here. But it's the probability of obtaining a head is higher now, based on our experiment. Okay, now we can use this posterior probability as a prior distribution for the next step. Okay, so we flip a coin once again. Then suppose we got a tail. Okay, so in this case, okay, so now we have the second toss. Only once we toss once, and we got a tail. So this means tail. Now our prior distribution is the previous posterior distribution. So the second posterior distribution, x2 is 0 and 2 is 1. And actually this information now includes the previous experiments. Okay, so now we have some constant times, so 1 choose 0 because we got a tail out of one flip, p to the power of 0, 1 minus p to the power of 1 minus 0, and times our prior now is 2p. This is the posterior probability we got obtained in the previous experiment, this one. So we use it as a posterior distribution for the next experiment. Then if you calculate this, you have a beta function 2 and 2 and p. So this p is here and this 1 minus p is here. So this is the second stage posterior probability distribution density function. Now we can use this density for the prior distribution for the next experiment. Okay, suppose we flip a coin for the third time and we got a head. So this is just assumption. So we got a head. We toss once and got a head. Let's assume. Then next posterior distribution. Is given by so some constant 1 choose 1, p to the power of 1, 1 minus p, 1 minus 1, and this distribution as the prior distribution. Okay, p 1 minus p, b 2 2. Okay, now this would be like after some calculation, it will result in beta function 3 and 2 and p squared and 1 minus p. Okay, and we can continue this on and on. So next experiment, So we use this as a prior and we get another posterior with a new piece of information, and we can continue this on and on. So suppose we keep flipping a coin over and over, and after 100 flips, so after 100 flips, suppose we got 52 heads and 48 tails. Okay, and if you continue the same process over and over, at 100th step, our posterior probability will be something like this. So p to the power of 52 and 1 minus p to the power of 48 divided by beta function 53 and 49. So what does this function look like? Here's the answer. So in the beginning, we had no information, so we assumed the uniform distribution like this. So it's a constant. So from from 0 to 1, it was a constant, just 1. Okay, and after the first experiment, we got 1 head and 0 tails. So after that experiment, our posterior probability looked like this. So it was biased towards head, right? So this probability density is higher at head and 0 at tail. Now, in the second experiment, we used this distribution as the prior distribution, and we assumed that we got a tail now. So our posterior probability after the second experiment becomes symmetric. We got 1 head and 1 tail, so there is no reason to be biased. So it is symmetric around 0.5. Okay, so the most likely value of p would be 0.5 because it will have the maximum value here. The posterior probability will have the maximum here. Okay, and the third experiment, we use this density as the prior density and apply the Bayes formula, and suppose we got another head. So again, in total we have 2 heads and 1 tail, so we are a little bit more biased towards heads. So the probability greater than greater than 0.5 has a little bit larger values than probabilities between less than 0.5, right? So we are a little bit more biased towards heads. And after, but this is not as biased as the first experiment. In the first experiment, the density was highest exactly at p equal to 1, but not anymore because we have some result with a tail. So we are biased towards heads, but not as biased as the first experiment. And if we continue this 100 times, and suppose we got 52 heads and 48 tails, then if we keep applying the Bayes formula, what we get is this curve. So this is more it has a sharper peak here around 0.5, but a little bit greater than 0.5, and the probability density around 1 or 0 are close to 0. Yeah, so it is more or less unbiased, but maybe a little bit biased towards heads because of our experimental results. So if you continue this over and over, the distribution will converge eventually. So probably it will look like very sharp distribution, something like this. If the coin is really a fair coin. But if it is biased a little bit, maybe it will have the sharper peak somewhere off the middle point, 0.5. So in this way, as we gain more experience, meaning we carry out more and more experiments, we can update our knowledge about the phenomenon. And that's what's nice about Bayesian inference. So as new data come in, we just update our knowledge one by one. Now let us consider another problem, which may be regarded as a kind of Bayesian version of the t-test. But it's actually completely different from t-test. But anyway, suppose we have a set of data. So these are independent observations of some random variable that are assumed to follow the same normal distribution with the mean mu and the variance sigma squared. Now what we are interested in is to derive the distribution of this mu. So what kind of distribution does this mu follow given this data? Okay, so the likelihood can be considered as a function of mu and sigma squared is given by this. So it's since these observations are independent, we just take the product of all these observations. Okay, from 1 to n, and each of these follow the same normal distribution. So we have the density function for the normal distribution here, and xi minus mu squared to sigma squared. Okay, and this means product. Just like let's see, just like this is a summation, a1 plus a2 plus and so on. This means a product. So this means a1 times a2 times up to an. Okay. So if you combine all these terms, because this is an exponential function, we have 2 pi to the power of n over 2 and sigma to the power of n, and exponential of the sum of these. Okay, to sigma they are the same, and we have this summation. Okay, so this is the likelihood. Now we want to introduce priors for mu and sigma squared. Okay, for mu we just assume a uniform distribution between some maximum value and some minimum value. Okay, so this is mu mean, and mu is between this minimum value and this maximum value. Okay, this is a uniform distribution. It will look like this. So this is mu, mu mean, mu max. So 0 and some positive value and 0. So this value is this. Okay. And for sigma, we assume some strange distribution like this one. Sigma is while mu can be either positive or negative, or it can be 0, but sigma must be positive. Okay, so sigma must be positive. Okay, actually we also assume this distribution from sigma minimum to sigma maximum, but the distribution is inversely proportional to the value of sigma. So the density function of sigma would look like something like this. Okay, but we limit this is max, but this should be sufficiently large, and this is sufficiently close to 0. Okay, so we assume these two prior functions, and also we assume that mu and sigma, they are independent of each other. Okay, then apply Bayes' theorem. So basically we have this likelihood times this prior times this prior is equal to the density, or the posterior density of mu and sigma given the data. Okay, so this will be proportional to this likelihood. So likelihood and this prior distribution for mu and prior distribution for sigma. Okay, so this will turn out to be something like this. So since this is just a constant, we can just ignore the constant term, and we have L divided, and this is proportional to, inversely proportional to sigma. So we have something like this. Okay, but in this particular problem, we are not interested in the distribution of sigma. We are just interested in the distribution of mu. So what we can do from here is to somehow eliminate the dependence on sigma. Okay, this can be done by integrating out over sigma. Okay, so we have this posterior density given data and some prior knowledge. It's not equal, it's proportional to and sigma. Okay. Yeah, you may wonder what happens to the proportionality constant, but that can be determined later. Since all we need to know at this point is that this posterior probability is proportional to this quantity. Okay, but we want to get rid of this sigma, and this can be done by integrating out over sigma, which means this. So this is equal to integration of this one. Okay, so mu sigma d sigma. Okay, we integrate over all possible values of sigma, so you substitute the definition of this. And so this is like L mu sigma squared and over sigma d sigma. And if you integrate this and just ignore the constant terms, this is proportional to something like this. Well, I think we should first write. So let's see. It should be some proportional to something like this. Xi mu sigma squared. Mu squared and over to the power of n over 2, negative n over 2, which is equal to this, mu minus x bar squared plus dash s squared, where I will explain what these are. And this is equal to 1 over n minus 1 mu over x and s over square root of n squared plus 1. Actually, this is not equal, this is proportional to. And this. And here, x bar is, of course, the sample mean. And s, this large S squared, is the sum of squared deviation from the sample mean. And this small sigma as s is its squared is defined by large S divided by n minus 1. So this is the unbiased sample variance. Okay, so this one corresponds to this one corresponds to this one. Okay. Now, if we substitute t equal to mu minus x bar over s over square root of n, then this follows the t distribution with n minus 1 degrees of freedom. Okay, but so this looks, so this is a t distribution basically, but this is here in this case the random variable is this. This is a random variable. But this is a constant. Okay, this constant is calculated from the data. Okay, but this mu is the random variable in this case. But if you compare this with the t-test, in ordinary t-test, which compares the difference between the sample mean and some constant, so some hypothetical, our hypothesis, right, of the mean. In that case, this x bar was supposed to be the random variable. Okay, so this x bar, its value can vary depending on the samples, right? So in that case, this was random variable, but this mu was a given constant. So it's quite opposite in this case. But nevertheless, we still have the density function of the t distribution, and this the distribution of this mean. which is unknown, uh, follows the t-distribution with n minus 1 degrees of freedom. Therefore, the density function of this t, so it's a t-distribution, so we have, after all, wait a minute, in general, the t-distribution has this density function. Gamma f over 2 and 1 plus t squared over f plus 1 over 2. So in our case, the degrees of freedom is n minus 1. And t is mu minus x bar over s over square root of n. So that's what we were looking for. Okay, let us summarize again. So in the ordinary frequentist approach to the t-test, which is comparing the sample mean with some theoretical constant, in that case, mu is the constant. So this is the theoretical value of the sample mean with which the sample mean is compared. And this x bar is assumed to be the random variable. So it depends. So this value varies depending on the sample. And the degrees of freedom was n minus 1. In the Bayesian case, this mu is the random variable. So we are trying to find the distribution of this mu. Okay, and this x bar is just a constant calculated from the given data. And the degrees of freedom is again n minus 1. So we define the t-statistic in this way. So it's the same in both frequentist approach and the Bayesian approach. No, these things are all the same. So x bar, s squared, and small s squared, they are all the same. But the meanings of mu and x bar, their roles are different. It's quite opposite. Okay. Let's summarize the difference between the frequentist approach and Bayesian approach again. In the frequentist approach, its approach is basically we put up a hypothesis, and based on the hypothesis, we calculate the likelihood of the observation. Okay, so basically we calculate the probability of data given hypothesis. For example, in the case of coin flipping, hypothesis means the coin is fair, for example. So P is 0.5. And based on that, we calculate the probability of obtaining 5 heads out of, let's say, 15 flips. Okay, and given that the hypothesis of that the coin is fair. And if this probability is very small, for example, in this case, we may calculate this probability using the binomial distribution. If this probability is very small, for example, less than 1%, then we reject the hypothesis that the coin is fair. And that was the approach. But if you think about it, since this probability is a continuous variable, so the probability, if we calculate the probability that the coin is exactly fair given whatever the condition, this should be 0. So it's impossible, basically. So So we are not sure if this argument is valid in this uh, in, in this uh, in this example. On the other hand, in the Bayesian approach, we don't just calculate the probability that this p takes a certain exact value, but we just calculate the density function or distribution of this uh, random variable given the data. So we consider the entire distribution of the hypothesis. Okay. So in this way, so for example, it is possible to calculate the probability that this p takes the value between 0.45 and 0.55, for example, given data. Okay, so this may not be 0 because it has some interval, right? So this looks more reasonable in my opinion. And in the second example about estimating the mean of the normal distribution, in the frequentist approach of t-test, we just assume this value. For example, the mean is, I don't know, whatever the value, 1.5, and we can apply the t-test. So based on the data, we calculate the sample mean, and we just use whatever the predicted value of this mu as a constant and calculate the t-statistic and apply the t-test. So if the probability of this t-statistic is small, then we reject the hypothesis that this mu's value is 1.5, for example. But since mu is a continuous variable, just one value doesn't mean anything really. So we should be really considering the distribution of this mu, and which is made possible in the Bayesian case, because in this case this is a random variable, and based on the data we calculate the distribution of this mu. So instead of mu being a constant, mu is a random variable. It's a distribution. It's not a bell curve per se. It's a t-distribution. So we can, for example, calculate the probability that mu is between this and this range by integrating this density function for the t-distribution. So we can pick any arbitrary interval and calculate the probability that the value of mu is within that range. So that is, in my opinion, more robust way to deal with this ambiguity, this uncertainty of this estimate.